Welcome back. In previous videos, we talked about logarithms and their applications, and we said, they can be used in science, in growth and decay, in compound interest, and a variety of other places. In this video, I'm going to show application of some of those formulas and where logarithms apply and help us calculate different things. You won't be asked to memorize these formulas. We will give all these equations to you. You just need to know how to input the correct variables and solve for the appropriate unknown. So let's begin with the compound interest formula. The compound interest formula listed below, A equals P times the entire quantity 1 plus R over N, all raised to the N times T, where A is the ending amount of money, the money you'll get after you earn your interest. P is the principal amount invested, or the beginning investment. R is the interest rate as a decimal. So, for example, 6%, you wouldn't use 6, you'd use the decimal 0.06. N would be the number of times interest is compounded each year. That is the number of times your interest is added back into your principal so it can continue to earn more interest. Okay, so how often the interest is added to the principal so your interest can earn interest. So quarterly compounding means your principal is added every quarter or 4 times a year to the interest is added to the principal 4 times a year. And T is the amount of time that you're investing in years. So if you're doing annual interest rate, it's T is the number of years. If you did a monthly interest rate, T would be the number of months. But normally we quote interest rates on an annual or yearly basis, so our time will also be. Let's take a look at a sample problem. Let's say we want to find the value of $2,000 invested at 5% compounded quarterly after 5 years. So how much money are we going to have after 5 years if we earn 5%? Well, that's not going to be, it's not going to be $100 5 times. It's going to be a lot more than that. So let's take a look and see. So we want to find A. We want to see what that dollar amount is. So A equals our initial investment is $2,000, invested at 5%, so it's 1 plus 0.05 all over N. It's compounded quarterly, 4 times a year, raised to the N times T. So 4 times 5. So A equals 2,000 times 1 plus 0.05 over 4 raised to the 20th power. I'm trying to add fractions in here, so 1, I'm going to change that really to 4/4. That's really what we want to add here. We want to add 1 or 4/4 to 0.05. So our amount equals 2,000 times, 1, so 4 plus 0.05 is 4.05 all over our common denominator, 4 raised to the 20th power. So there we go. That's all we need to do. And I'm going to go back to my calculator, and I'm going to input my information, 2,000 times the quantity 4.05 divided by 4, all raised to the 4 times 5, or the 20th power, and we get $2,564.07. So $2,564.07. Sample 2 says find the number of years it will take for $500, paying 8% compounded quarterly, to double. Well, if we're going to double 500, 500 times 2 is 1,000. So our ending amount, we already know it's going to be 1,000. Our beginning amount is 500. It's our principal. And we're going to add 1, and we're going to pay 8%, 0.08, all over n, the number of times it is compounded, all raised to the n times t. So 4 times t. Well, we don't know t. That's what we're trying to find, is the number of years. So I could divide both sides by 500 right away. Right? Don't we want to have twice as many dollars as we had at the beginning? So this is just going to be 2 to 1. Right? Divide by 500. 1,000 over 500 is 2. We're left with 1. I need a common denominator here. We're going to use 4 again. So 4 over 4 plus 0.08 over 4, all raised to the 4t. So now what do? I've got t up in the exponent here. So what we can do, what we've learned previously, if our variable is up in an exponent, we can take the logarithm of both sides. So I'm going to take the common log base 2, and I'll log this side, log of, well, that's 4.08 all over 4, raised to the 4t. I can apply my properties of logarithms. Log 2 equals 4 times t, log base, and 4.08 over 4, hopefully you know that. You can recognize that. That's 1.02, isn't it? So we want to solve for t, so we can divide both sides by 4 times log 1.02. So we should have t equals log base 10 of 2, all divided by 4 times log base 10 of 1.02. And I already know, and I know an general investment rule for doubling, so I have a pretty good idea what this answer is going to be, and I'll teach you that at another time. Maybe we'll talk about that in class. But let's go ahead and pull out our calculator, and we want to take log 2, all divided by, I'm going to use parentheses here just in case, 4 times log of 1.02. Close my parentheses, double close there because I had 2 to open. Right? So 2 to close. And I get 8.75. So it's going to take 8.75 years. 3/4 of a year would be 8 years and 9 months. Another kind of compounding is continuous compounding. Our continuous compounding formula is A equals P times E. So there's that E again, that number, raised to the R times T. So we're probably going to use the natural log on this one, where A is our ending amount again, P is the principal invested, R is the interest rate, and T is the amount of time in years. Now we don't have to worry about compounding because we're compounding continuously. So that means we add your interest to your principal as it's earned. We don't hold it for a while and then add it later on. It's just compounding and compounding and compounding. It's always being continuously added to your principal amount. So it says redo sample 1 using continuous compounding. How much more money do you earn with continuous compounding over quarterly compounding? Right? The more often the money compounds, the more you have principal to earn interest on, so you better earn more interest with continuous compounding than you would with like quarterly compounding, assuming you have the same rate. So let's take a look here. We invested $2,000 at the beginning. We want to find our ending amount. So our principal is $2,000. E to the R, and our interest rate was 0.05, and T is 5 years. So 5%, 5 years, but now compounded continuously. So, well, looks like we can probably go right to our calculator. This looks like it's calculator ready. Go to my calculator, and I'm going to type in 2,000. E is right here. It's above the natural log symbol, so second natural log. So E, all raised to the 0.05 times 5. Let your calculator do the work for you here. And we get $2,568.05. $2,568.05. So it looks like we earn about another $4 over 5 years. $3.98 additional. So good deal for you. We also see logarithmic equations in exponential growth and decay. Here we have the formula for exponential growth and decay. Y equals y sub 0. Y sub 0 is our original amount. Y is the ending amount, or the amount of substance remaining. E, okay, our number in honor of Euler, the 2.78 number. Okay, and K is going to be some unique constant. It's going to be different for every different kind of compound. Okay, we'll give you K. You don't need to worry about that. And T is time, and again, usually in years. So if we do this sample 3, a radioactive substance decays to the function defined by y equals y sub 0 e to the, now here's our K, negative 0.0239 T. If the initial sample contains 12 grams of radioactive substance, y sub 0, how many grams will be present after 35 years? So y equals 12 times E raised to the negative 0.0239 times 35. And it's that straightforward. We go to our calculator, 12 E raised to the negative 0.0239 times 35. And we get 5.1986. I'm going to call that 5.2 years. Pardon me, 5.2 grams. What is the half-life of the substance? So the half-life meaning how many years will it take for a quantity to be cut in half. So we're going to go from 12 grams to 6 grams. So we already know that y is going to be 6 grams. It's going to be half of the 12. So we could do 6 equals 12 E negative 0.0239 T. We could make this 1 and 2. That's a half-life, isn't it? So we could say 1 equals 2E to negative 0.0239 T. Well, this one, a little bit different. Our T is up in the exponent, so we have to solve this like we solve a logarithmic equation. Okay, so we want to take the, now we're going to use the natural log because we've got E here. So So I divide both sides by 2. I have 1/2 equals just plain old e to the negative 0.0239t. And now I'm going to take the natural log of both sides. Take the natural log of this side and the natural log of that side. So we get the natural log of 1/2 equals the natural log of e all raised to the negative 0.0239, which is the natural log of 1/2 equals negative 0.0239 t times the natural log of e. And hopefully we know the natural log of e is 1. So the natural log of 1/2 equals negative 0.0239 t. We divide both sides by negative 0.0239. And we'll get t equals, put this back into our calculator, the natural log of 1/2 all divided by negative 0.0239. And we get 29 years. T equals 29. And that, think about that, that totally makes sense. Because if it took 35 years to get to 5.2 grams, wouldn't it have to take less than 35 years to get to 6 or to go from 12 to 6? So that sounds just about right. And there's some applications of logarithmic formulas, and we will see you in class.